Greetings, I'm Vladyslav Holdovanskyi, and I'd like to extend my gratitude to the organizers for giving me the opportunity to speak at this workshop, and to all of you for watching this presentation. The topic of our work is the determination-based correlation coefficient. Correlation analysis has been around for over a century, but new correlation coefficients or their applications emerge annually. This demonstrates the relevance of the tool. In our work, we examine regression from the perspective of stochastic functions. Let y be the target feature by formula, where z is a random variable, noise, x is an independent feature, and the dependence phi of x is absolutely functional and deterministic. Characteristic of stochastic functions convert random noise into a constant, leaving the function unchanged. Obviously, we want a similar tool for regression and correlation tasks that filters out noise and retains functional dependence. In our article, based on the characteristic of stochastic function, we arrived at the following grid, which will approximate the stochastic function. These graphs show the approximation of stochastic functions by the grid. Blue dots represent synthetic data, the red line is the real function, and orange dots are interval centers. As we can see, the grid approximates function well. Based on our grid, we arrive at the following correlation coefficient. Essentially, we calculate the ratio of local unaveraged variances to the total unaveraged variance. In research and literature, we found a similar measure, the correlation ratio, mentioned by Fisher and Pearson. It is used in variance analysis as analog of ANOVA and sometimes referred to as a correlation coefficient, but we have not encountered its use for estimating potentially explained variance. Based on the similarity of the coefficient to the coefficient of determination, we interpret our coefficient as the proportion of explained variance of y through x, even before building and even choosing a machine learning model. This allows us to assess the potential of the data and consequently the model even before selecting the model itself. Let's consider the criteria by which correlation coefficients are compared. Using the table from the randomized dependence coefficient article, we compared our coefficient with others. Our coefficient outperforms all others except RDC, as our coefficient does not satisfy all Renyi's properties. However, it is worth noting that properties 1 and 4 are partially satisfied, which is sufficient for practical purposes, and property 5 could potentially be addressed. In first experiment, we compared the efficiency of our coefficient with the Pearson correlation coefficient as the fastest classical one and RDC as the main competitor. In the RM environment, our coefficient outperformed RDC. Pearson was faster, but our coefficient scales also well. With 10 billion data points, the algorithm executes in 1.42 seconds. In second experiment, we attempt to find the optimal parameter n for different amounts of data. For synthetic data, we could compute the coefficient of determination since we knew the real relationship function. It was found that accuracy depends on the rate of change of the relationship function. Also, the error for 1,000 points was not significant. In the third experiment, we researched the relationship of our coefficient with the coefficient of determination and the Pearson coefficient under different noise levels. The graph shows that our coefficient approximates both well. Moreover, for linear dependence, the graphs almost coincide. The practical use of our coefficient is to assess the proportion of explained variance before model building. This allows understanding whether it is possible to improve the existing model, how accurate a model can be built on the data, and whether it is worth building a model at all. Our coefficient is not perfect, but has the potential for application in machine learning. It outperforms most other coefficients in all criteria except for Renyi's properties. High efficiency allows using it with big data. Interpretation provides important information for building regression models. Thank you for your attention.